8.2, power of recursive algorithms. Okay. The problem is the old one. Everyone here familiar with that? Yeah. Oh, yeah. I already switched. That side so slow. Yeah. Right. I don't know. Yeah, it takes so long. More than 10 seconds. Yeah. That's so bad. Yeah. Oh, this time, yeah, let's still, how long? Well, yeah. All right. Yeah. So we do not have much time. Yeah. To solve it. Yeah. Let me see, to solve it. Yeah. Okay. Yeah. All right. Yeah. Let me see. All right. Yeah. Well, this time faster. Yeah. The problem 9, the Tower of Hanoi. This one, as I remember, in first, you must, have experience solving this problem before, right? Yeah. It's a puzzle problem, interesting puzzle problem. Yeah. All right. So let's try to use recursion. Here we use the recursive understanding to solve this problem. Yeah. All right. Yeah. So now it's much faster. Yeah. All right. Here I use a 3-disk case to explain the rules. Yeah. But our general solution, we need to apply on n disk, not 3-disk. Okay. Yeah, 3. So here, with the 3-disk version of puzzle, so let me give you the rules, 3 rules to solve this puzzle. Yeah. First, only 1 disk can be moved at a time. Every time you can move 1 disk from one pole to another one. Okay, you have 3 poles. You can only use those 3 poles. Okay, you cannot increase another pole. Yeah, only 3. Yeah. Number 2, a disk. Oh, number 2 still not there. Yeah, a disk cannot be placed on top of a smaller disk. You have to follow the order. Smaller disk must be on top of larger disk. You cannot, reverse that way. Larger disk on top of smaller disk. So rule number 2 does not allow you to do that opposite way. Okay. All right. Rule number 3, all disks must be stored on a peg except while being moved. Yeah. So when you move, it's okay. So you hold that disk for a short time, then you place it on another peg. All right. But you cannot put it on the table. All right. You cannot put your disk on that board table for a temporary storage. Otherwise, it's too easy. Yeah. So when you put it somewhere, it must be on one of the 3 pegs. Okay. Yeah. Following all these rules, now let's solve this simple case, 3-disk case, to move the 3 disk from the first peg to any of the 2 empty pegs. How many moves do you need? Following these 3 rules, how many moves do you need? That's the question, puzzle question. Okay. Yeah. And our final solution, we need to consider n-disk case. N-disk case. Not just 3 disks. But 3 disks, you get an idea to solve n-disk case. Yeah. So 3 disks is good enough. Yeah. All right. Yeah. Here, yeah, because I have 5 minutes. Oh, not 5. Oh, yeah. 20 minutes. Yeah, we can complete the solution. Yeah. Although a little slow here, display. Yeah. Here I give you the reference, not analysis part. Yeah. how to solve the general problem with n disks. That's our goal. Yeah, still not there. Yeah, you just hear my talking. I'm talking. Yeah. All right. Okay. So when we start, remember our old strategy. Start with some simple cases, smaller problem sizes. Yeah, that's our old strategy. Yeah. All right. How about we consider n equals 1 or 2 case? N equals 1 is trivial, right? Yeah, n equals 1, trivial. Yeah. Okay. N equals 2 also very easy, right? Yeah. Okay. Yeah. So here we can assume we have the solution of n equals 1 and n equals 2. Yeah. Now let us work on n equals 3. Okay. Yeah. So when we solve problem of size 3, we can assume that we already have the solutions for size 2, the previous problem size. We have it. This assumption is fine, right? Because we know the solution. So we do not make some, too aggressive assumption. Yeah. So this assumption is reasonable. Yeah. Okay. All right. So here, that means we can use recursion. Yeah. You have solution for n equals 2. Now you only need to consider the difference between n equals 3 solution and n equals 2 solution. What is the difference? If you know that part, then you have a recursive solution. Okay, yeah, all right. So here, we know n equals 3, you need to make many non-trivial moves. Yeah, so you can play around a little bit, several non-trivial moves. Yeah, yeah, but here, let us work on this 3-disk version first to get some experience. Yeah, we need that experience. Okay, yeah, all right. Here, I use diagram to do experiment. Yeah, so here, the diagram, okay? So when we start, yeah, this is the starting point. So when we start, step 0. In step 0, we have this state, okay? Yeah. Now, our next step, okay? All right, next step, move the smallest disk to peg 3. That's legal, right? Yeah. The rule, 3 rules, no violation here. All right. Then our next move, the middle disk, we can only place it on peg 2. We cannot place it on peg 3. Yeah. So our next move must be like this. Okay. Yeah. Then the next move, we can only move the smallest disk back to peg number 2 or peg number 1. Yeah, if you like, you can move peg number 1. Yeah, yeah, peg number 2 and peg number 1. Okay, yeah. But we move it to peg 2. Okay, then peg 3 is empty, so we can move the largest disk to peg 3. Okay, yeah, yeah. So here you can see we have the solution P of 2, disk and size 2 solution. Yeah, you move 2 disks from one peg to another peg, size 2 solution. Okay, here you see that. All right. Then step number 4, we move the largest disk to peg 3. Okay, so no violation. Yeah. All right. Then after that, we need to move these 2 disks to peg 3 with another P of 2 solution, right? Move 2 disks to one peg to another peg. Okay, yeah. All right. So we need another P2 solution to get a whole P3 solution. How about that? Yeah. Try to get understanding of this step. All right. But to do it, we work all the details of P2 solution. The smallest disk, we move it back to peg 1. Then the middle disk, move it to peg 3. Then the smallest disk, move to peg 3. And we get a whole solution. So you can see we need to make 7 moves to solve this disk 3 problem. We need to move disks 7 times. Solution. Okay? Yeah. All right. All right. Question. How do we generalize the solution to n disks? Yeah. We need to get an n disk solution. Now we need to, using the similar idea to get an m disk solution, our final version of the solution. Okay, yeah, all right. So let's start over again, but this time we imagine we have n disks. Okay, yeah, all right. Yeah. So we use recursion to do it. Yeah. Yeah. So when we work on P of n, we assume P of n minus 1 solution is available. We can use it directly. Yeah. All right. To solve a problem of size n, we can reduce it to problem of size n minus 1. Yeah. Although we need to do a lot of steps for P of n minus 1, but we assume we have it. Okay. Yeah. Not start from scratch. We start from P of n minus 1. Okay. Yeah. All right. So here in the diagram, we, revisit this arrangement here. Yeah. And but we assume we have that n disk stack. N disk. Imagine the pile has n disks. Yeah. All right. Yeah. But when we move, assume P of n minus 1 is available. So we can apply that P of n minus 1 directly. Okay. And we do not need to go through all the details of P n minus 1. So we can ignore temporarily the details of P of n minus 1. We hide the detail. Okay. Yeah. But later we can go back to the details. But at this point, high level, this understanding, we can bypass the details. All right. Yeah. All right. To solve P of n, yeah. Because P of n minus 1 solution is there, we can apply it. Yeah. So let us apply P of n minus 1 directly to move the first n minus 1 disks to one of the 2 empty pegs. How about that? One of the 2 empty. That's the known solution, right? P of n minus 1, known solution. The detail, we don't worry. At this point, we don't worry about the details. Later, we know we can recover the details, but not at this point. Okay, yeah. Then we can move the bottom largest disk to peg 3. Yeah. Oh, what's that? Yeah, yeah. Anyway, yeah. Let me just draw. All right. The bottom disk to peg 3. Okay. Then let's apply another P of n minus 1 back to that peg 3. Another known solution, P of n minus 1. Then we get it done. Okay. Yeah. So here, as a summary, yeah. Step 1, apply that P of n minus 1. Okay, from first peg to second peg. Okay, yeah, from first peg to second peg. Okay, and step 2, move disk 3 from first peg to third peg. Okay, step 2. Yeah. Step 3, another P of n minus 1 solution, but this time from peg number 2 to peg number 3. How about that? Right, it's done. Okay, so here you can see we intentionally hide the details of P of n minus 1 because we have the confidence the details can be recovered later. So we don't worry about the details. So we just, take the whole package, P of n minus 1, the whole package, and we apply it. Okay, that's our step 1. Then we move the bottom disk. Okay, so you have to do fill in the gap. That's the gap portion. Okay, after that, you need to move those n minus 1 disks back to the destination peg. Okay, yeah, that's recursion. Yeah. All right, based on this recursive understanding, our pseudocode we can write in this way. Okay, move disks function implementation. The first parameter, number of disks. How many disks do you have? Okay, yeah, so you can put number there. 100, you just put 100 there. Okay, yeah, n disks, the number n, yeah, first parameter. The second one, after the first parameter, the last 3 parameters for the numbers for 3 pegs, peg 1, peg 2, peg 3, the numbers for the 3 pegs. Okay, all right, so then your implementation, you call this function recursively. Okay, yeah, if the number is greater than 0, not empty, yeah, so you have some disks. Okay, then you can implement the steps recursively. Yeah. Move disk n minus 1, but you need to make your peg numbers arrangement carefully here. Okay, from peg, temporary peg, to peg. Okay? The destination is that 2 peg. Okay, yeah, I mean third. Yeah, the positions carefully. All right, then output C out. Yeah, output, you print a message representing you move the disk, you do the work of disk moving. That's the explicit work of disk moving. Okay, the output. Yeah, then another recursive function call. Yeah, still n minus 1 disk, but you need to change some peg numbers. Okay, carefully choose the peg numbers to set the destination, the source, destination, temporary peg correctly. That's the whole solution. Yeah. Now, the summary of the solution. Now, first, we know this puzzle question is relatively hard, right? Yeah. If I give you 10 disks to solve this problem with 10 disks, you need to do quite some work, right? A lot of work, quite some work. Yeah, it's not easy. Yeah. But the implementation code, less than 1 page, these are a few lines. We can implement this relatively hard solution in these a few lines. How powerful is this recursive algorithm? Now imagine without using recursion, how can you do it? I cannot do it. So I myself, I cannot do it. I cannot imagine. How do I write, all the moves? Okay. Yeah. I will get lost. Okay, yeah. But with recursion, you can do it as easy as this. That's the power of recursion. From this example, we have chance to appreciate the power of recursion. Not just for this one. Later, we have many such questions. If you do not use recursion, so hard to solve. But with recursion, much easier to solve. There are a large number of such computing problems. Okay? Yeah. So definitely we need to practice this recursive thinking well. So then in future, when you some appropriate computing problems, you may need to apply this recursive approach, especially for relatively hard problems.